So welcome back to this Machine Learning 1 course. And we shall pick up where we left off. But before we do that, I'll give you a quick reminder of where we left off. And that was something along the lines of, we're trying to formulate this whole machine learning problem that we're trying to solve. Or maybe I should say the setting. This is what people usually call it. It's like the, they'll write in your papers and your textbooks, they'll be like, this is the, the supervised learning setting. It's defined by you have this data set. Your objective is to design a learner such that it will produce a predictor that will predict new, labels correctly based on new features. And we're going to, our goal is to define this setting because, without formally defining it, who knows what we're trying to formally do. Okay, so to do that, it turns out you need math. And so we learn math. So that's what we were doing last time. We were learning a lot of math. Mainly because when I tried to motivate this, I gave you some definitions of what the data set might look like, what a function that predicts things might look like, what a learner, which is a function that takes in data sets and produces predictors, might look like. And we wanted to learn how to define these objects because they'll be important. So we started off on our little journey, defining sets and operations with sets. And then after that, all sorts of other objects. I don't know, tuples, which are ordered sets that can have duplicates. And we talked about this very important thing called the Cartesian product, which is I guess this is kind of incorrect what I have here, which is it's not creating tuples, it's creating sets of tuples, right? And maybe let me remind you because this was important. So the Cartesian product is an operation on one or more, well, it's actually an operation on two sets, but you can do it multiple times. And so if you have a set omega and another set calligraphic x, the Cartesian product is you put this times symbol, the x in between, and it takes these two sets, which here is cat and dog and 0, 1, and 2, and it'll literally just create a new set, which is all the possible ordered pairs of the two. But importantly, the first element comes from the first set and the second element comes from the second. So these are all the ordered pairs. Unsurprisingly, since the sets have 2 and 3 elements, there's going to be 2 times 6, or 2 times 3, which is equal to 6 possible pairs. And so, yeah, order matters. And this will be important because, we're going to construct all sorts of things that are tuples, such as these feature label pairs. And so the features will be the first part, the first set of features, and then the other part will be the labels. And it's going to matter that the first thing is the features and the second part is the labels. And I guess it looked something like this. It's going to be the features might be two-dimensional vectors. The labels might be just real numbers for these regression problems where you're predicting the price of a house. And then you'll get a feature label pair that looks something like either this or this, depending on how you want to write it. This one maybe is more I don't know, obvious what's going on. This is your feature, it's two-dimensional real number, so it's a vector. And this guy right here is just a real number. Okay, anyway, so order clearly matters. And then we moved on to things called vectors, which you can roughly think of as these tuples that you can then add and multiply. And for the purposes of this course, all you need to remember is that vector spaces that we're going to deal with are the reals or the two-dimensional real numbers or three-dimensional onwards. In general, it's going to be these d-dimensional real numbers, which is going to stand for the fact that we have d features. And yeah, so you can do operations with vectors, right? You can if you have a vector x, which is two-dimensional vector, another vector y, you add them like this. You just add the corresponding dimensions or indices. And you can multiply them by scalars. So the scalar just multiplies each dimension. Okay, you probably know all this already. And then there's operations like transposes and so on and so on. And there's dot products, which will be important because this will be able to, you can multiply two vectors actually together, and it will kind of tell you how aligned they are. And in the very simple case, which maybe I didn't show here, is in the one-dimensional case, then x it would just be x times w. And you could think of this as just like a line with a y-intercept of 0. So like the w could be like the slope of the line. Okay, and then there's matrices, which you can think of just a bunch of vectors stacked as rows. And then you multiply matrices and vectors the usual way. Okay, let's get to the stuff we were last time, which is functions now. So as you see, functions are a very important part because they are going to define the learner and the predictors. And so we just want to get used to like, you know, what a function is. And at a higher, like, I mean, I guess more than at a high, like the formal definition of a function is just something that like maps objects from one set to another. And that set can be anything. Like that set can be, you know, something simple like numbers, but it could also be like the set of all data sets. And you can map to anything you want. That set can also be simple like the real numbers, or it could be a set of all functions, or a set of specific functions, like maybe just the lines, like all lines with all slopes, you know, or maybe all like quadratic functions. And this will be important because at the end of the day, we're going to want to have a function or predictor that somehow like, you know, predicts new things. And then the question is going to be like, well, what functions do we pick for it to be? Maybe do you want to like, does your learner want to search over all functions? Should it search over less than all functions? And we're going to see trade-offs in these things. Okay, so now let's define things. So this is going to be the notation we use everywhere, and this is standard. So a function is written as like the function, I guess, definition f, and then you say it's a map from this set x to another set y. Notice these are sets, and your function should take some value for every element of this set, and this is called the domain. I guess that word makes sense. It's like, yeah. And so for every element of the domain, the function maps to some value, and the value that the function will actually map to. So for instance, like f of x equals 1, the actual values it maps to is called its range. So if we look at this picture, f will map to like some set of numbers. Here the range would just be 1. And so that's the range of the function, the values it actually maps to. And this object here right here is called like the codomain, which is at least as big as the range, but it could be bigger. And to be honest, some people just call these things the same thing. Okay. So let's look at some examples. A super simple example that is just literally, if you have a function, a super easy way to define what a function is for every single possible input it could take, like every value of the domain, just tell me its output behavior. And this is great when you have a small domain, but it's going to be a problem, obviously, when the domain is very large. So if your domain, for instance, here in this example, is just like the numbers 0, 1, and 2, all you have to do is define the function's behavior on these 3 numbers, and you're done. So for instance, here's a definition. The function maps 0 to 1, 1 to 2, 2 to 2. Fine. I can call the codomain all the natural numbers, right? But its actual range, like the values it can take on, is the set 1 and 2, because it only takes the numbers 1 and 2. And so the picture, this is what people love drawing these pictures, and I think they're quite helpful. Like, you can see what's happening here. You have a function, its domain is the numbers 0, 1, and 2. It maps to numbers 1 and 2. You can see that there's multiple values in the domain for which it maps to the same number, like 2. And that's a subset of this whole like codomain thing. Okay. But a lot of time we get interested in functions that are not just over these what are called finite sets. We want to talk about like infinite sets. And so one infinite set is the set of all real numbers. And we want a function that maps, you know, this all number, like maps real numbers to, let's say, real numbers. And you can imagine we already run into this issue where like defining the function one domain point at a time becomes a problem. And so there we just like, instead of doing it like the 1-by-1 definition, which I said here, which is mapping 1, we can just say like, oh, you know, for like we give a variable for the element of the domain, like x here, and we just say that the corresponding output is going to be some like operation that it performs on x. And so then there's like the x squared function. And so here's your function. Okay, this is probably a very elaborate way of saying like things you thought were absolutely obvious in like high school, but you'll see, you know, the domains and the ranges or the codomains get more complicated in a second. Okay, I just mentioned There's other functions. There's this thing called an exponential function. The exponential function is, you take one thing, it'll come in a second, but like the exponential function is this, like e is a number. It's defined in various ways. It comes up in all sorts of places in math. But for us, the exponential function is always going to be like e, this number, to the power of x. And it looks like this. Yeah, okay. Another important function that you should know is this logarithm function, okay? And throughout this course, when I say logarithm, I don't mean base 10 ever. We always mean the natural logarithm. So this is going to be the mapping we use in the course, which is the logarithm base e, and the natural logarithm, this notation is going to be the same. And so I'm probably going to like log without the e at the bottom quite often because I'm just going to forget. And this is just, I don't know, some of the math people like just, these things mean the same quite a lot of the time. So log means natural log, and it looks like this, and it will come up in some places. And like, I don't know, how you read the log. Well, the log should be read as like e to what power gives me the value inside the log, right? And so it's like the inverse, it's exactly the inverse of this exponential function. And so this is, if your function was like the log of the exponential of x, then you just get x back. And the reason why is like, let's read this, in English. The logarithm says e to what power will give me the thing inside? Well, I know e to what power is going to give me the thing inside, exactly the power that e is raised to inside. So it's going to be x. So like, yeah, that should make sense. Okay. These are probably like the only functions you're really going to need to know. So like you're going to need to know the polynomials. So we saw like x squared. You can raise it to like the power of 3, 4, 5. And you should know the logarithm and the exponential functions. Okay, now let's get into some more fun stuff. So these are going to be functions that have more interesting codomains than just real numbers. So now we're going to talk about the set of, the codomain being a set of functions. And remember this set builder notation we defined earlier, right? So here's a function g. It's mapping numbers to some other set. So it's mapping the set of real numbers to some other set. This set is the set of all functions, and it is to be read as, this is the set of functions such that these objects f are themselves functions from x to y, whatever they are, okay? And I could like, if I just cared about, let's say, lines, then I would add like an extra condition, which I won't, but I would add an extra condition saying like, and f of x is, let's say, exactly 2x or something like that. Or that would be one function. Maybe I should write something like, and f of x is equal to like wx, and w is an element of the real numbers. So this would be like all lines, something like that. Okay, so let's look at the example here. So what's an example of a function that maps real numbers to functions? Well, I can define anything. So here's an example. I have this g of z function, right? It's going to take in a number z, and somehow it's going to use that z to map to a function f. And this f will change potentially as the input changes. How does it change? Well, here's the definition. My f of x is a function, right? It itself is a function over some potentially other domain, like x. And so here's the definition of my function f of x. Right, f of x is just going to, it's like, or what is sometimes called like an indicator function. It's equal to 1 only if x equals z, and 0 everywhere else. So let's just look at the picture. So this function f of x is going to equal only 1 when x equals z, so that's going to be this point, and 0 everywhere else, right? Okay, and the important thing is like, how is this point determined? How is the point at which it's equal to 1 determined? Well, that's based on the input of the original function. And I don't know, like, this is not quite the data sets we're going to be working with, but you could imagine like maybe somehow your data set is just one number. Well, here's your function. It's like you get this one number and you output a function which just, it looks like this. And so if this thing was different, like if we were looking at like g of 2, then g of 2 would have like the value, would take on the value of 1 over here and 0 everywhere else. Okay. So this is an example of a function that outputs functions. And now let's get into the fun part, which is what we have for our learner, right? Our learner takes in data sets and outputs functions. So the definition is simple. Like the thing on the left, the domain, should be the set of all data sets. And we've already talked about how to define that. That was this object here, right? And that is to be read as something like the inside is the set that contains all feature label pairs, right? And we have n feature label pairs, so that's why we exponentiate to n. So we take the tuple that is of length n, or the set of all tuples of length n. Okay, so once again, this is the set of all data sets. And this is your codomain, which is like the set of all functions. And so now I've already given this example earlier, but we're gonna review it again, maybe with this new notation so it makes more sense. But this is like the kind of the learner that memorizes the data set, okay? Roughly speaking, what's gonna happen is your learner, your A, is gonna take in a data set, and the function it's gonna output is the one that, if you get a new feature, you look at your data set, does my data set contain the feature? If it contains the feature, then I just output the corresponding label. If it doesn't, then I just output some arbitrary number, such as 0. So maybe let's look at the plot first, and then we look at the definition. And so yeah, I guess this is going to be very important because this is like the first example of some learner. Once again, maybe not a great learner, but good to keep in mind how this is working. So here's an example where you have 2 data points. Okay, so your learner is taking in a data set with 2 data points. I can see there's 2 data points because there's this guy and this guy. Right? Each data point consists of a feature. It's a feature label pair. There's just one feature and one label here. And so I have 2 of these feature label pairs. So what is the corresponding function it produces? Well, the function is going to do the following. It's going to be, this is the plot of the function. This is f of x. Maybe I should put this like, oh yeah, this is f of x. And the way it behaves is, okay, for every single point in the domain, right? This is my domain x here. I'm going to look, in my data set, do I have that number? So like I can look here, it's like, maybe this is like 0.5. In my data set, do I have a feature that's 0.5? Well, no, I only have the features 1 and 2. So what do? I just output some arbitrary constant. That's going to be 0 here. So it's just 0 everywhere. And then I get to like a feature that I do have in my data set, such as 1. And then I will output what I have seen in my data set, which is 2. And then everywhere else, I still output 0. And then I get to another feature that I've seen, 2. It might be like houses with 2 rooms. And then I output a corresponding label, which is what I've seen in my data set. So once again, all you've done is memorize your data set here. Obviously, you're going to want probably something that doesn't just predict 0 everywhere, maybe something like a line. And as the data set gets bigger, we're going to talk about this. And yeah, I mean, formally, this is the definition we have already seen. It's just like, based on the data set, you produce a function. That function is going to be defined in this like what is called like a piecewise manner. And the definition is just you output your label if you have the corresponding feature in your data set, and otherwise you output 0. Okay. Any questions about this learner thing? Okay, great. In that case, we move on to a couple more concepts. Okay, there's these things called continuous functions. To be honest, I don't even think we need this that much, but it's here. And like, we're not even going to define it formally, but like, it's just like, if there's no abrupt jumps in your function. So like, x squared is continuous, the line is continuous. If you have something like this, if there's like a jump, there's a formal definition for this. We don't need it. If you have some jump like this, then it's called not continuous. Okay, so I need to know. Okay, let's get into some other actually important things regarding notation that will be used a lot. You've probably seen this integration stuff, and summation you've probably seen too, but there's like summation notation that, at least when I took 2 years ago, a lot of people seem to be confused about. So I just want to make it absolutely clear what the summation symbol means and how it works. Okay, so sometimes you want to sum more than just like a few objects, right? If you just want to sum like all the objects in the set 0, 1, and 2, then okay, you can write 0, 1, 0 plus 1 plus 2. And that's fine. But as you can see that when the sets start getting bigger, this is going to be troublesome. So we're going to define some like unified notation to make this more compact. So this is the symbol. It's this capital sigma, I guess, is what the symbol is. But this means sum. And then you have to define what objects are you summing over. And that's put in the subscript like this. So it'd be like you're summing over all of the elements of the set X, which in this case would just be 0, 1, and 2. You get 3. Okay. And in here, you can actually plug in functions. So you can see this is starting to get a little bit more, useful and complicated. So if your function is like x squared, then you can plug in, f of x here, and then you sum over, f of x with the value x from the set calligraphic x plugged in. And so you would get like 0 squared, 1 squared, and 2 squared. Okay, still probably seems quite easy. But you can get like longer sets. So here you see like we have sets that have some arbitrary length n, kind of like our data set might be, We might want to somehow sum up all the labels in our data set or something. But here we just have like n numbers, let's say. And in particular, this is not just any set, it's a tuple. It's going to be this ordered set of duplicates. And when we talk about tuples, which we will, as you can see in this course quite often, there's another way, another shortcut for the sum notation that people often use. Okay, so notice that since your set can be ordered, it is ordered, and you will often index the variables in your set with subscripts like this, then people will write the following, which are equivalent. So let's just see the old notation I was just mentioning. So you can write this, right? You can just say like the sum over all x in your set, and then that will just mean x1 plus x2 up to xn. But alternatively, people will actually write like the sum of the actual things in the set, like these xi's, and then you have the sum notation, which is like going from I equal 1 to n. And these are identical. So this notation will be used synonymously throughout. Okay, and yeah. And so this will be useful. And then when we get to continuous sets, such as like intervals and real numbers, we have to actually move to integration. And roughly speaking, it's because you can't really like order your sets if they're what are called uncountably infinite. We've seen this. And then like writing something like this, like x, if you write something like the sum of x element of the real numbers, that's like mathematically undefined, because like to write the sum, you have to define like how are you summing things up and like what order, and there's no way to actually write it like an ordering of the real numbers, and you run into some problems. So we move to integrals for these uncountable things. And you've probably seen this in calculus courses. And yeah, that's all we need to know, that if you want to like what is called sum up or like accumulate uncountable or continuous sets, then you're going to use integrals. And like the same kind of story applies. So like with the function that I guess we saw above, where f of x was this like x squared function, then if you want to like, let's say, accumulate the values between some interval a and b, you write the following notation, which is like you integrate from a to b over your function, which is actually equivalent to also just putting in the subscript the set you're integrating over. Yeah, the picture is the following. Like if you have x squared, it just means like take the area under here. Okay, and there's a question. Yeah, so okay, the question is asking like back to this piecewise function story. It's like there was this definition saying that like if you have a feature in your data set that matches the corresponding feature you're trying to like, I don't know, produce a value for, then what does this pick the lowest index mean? And this just means like in your data set, you could, here's an example, you could have had one more point. It could have been like 2, 4. Right? And imagine it came before this point here, which is totally possible. Maybe you had a house with 2 rooms that was like, let's say this meant $400,000. And then here you had a house with 2 rooms that had $300,000. That's totally fine. Like houses, with 2 rooms can go for different prices. Then we need to produce a function, and a function needs to produce one value for your corresponding input. So we have to pick which feature do we use, and just like arbitrarily we pick the feature that comes first in our data set. So we would use this. So for the house with 2, you would now, instead of outputting 3, you would output 4, because that comes first in your data set. And that's just to resolve this like minor conflict. An alternative is you could like average overall houses with 2 rooms, probably a better idea. And yeah. Okay. So let's just continue with finishing this math thing. Okay, so we talked about like accumulating, summing up quantities. Another operation we use is called the derivative in calculus, which tells you roughly the rate of change of a function at a particular point. it's denoted by, like, if you have some function f of x, you write this prime, f prime, and that means the derivative of x. And I'm not gonna, this is like the thing I expect you guys to know, which is that, you know, there's the derivative of like x squared is 2x. That's my expectation. And there's this other notation, like this d of f. I think this is called like Leibniz notation. That means the same thing as f prime. And sometimes you'll see this because it's more convenient in certain places. So these are identical. And so you should think of it as like f prime at 1 tells you that the slope at point 1 is 2. And that's like the line with the slope 2. Okay, and then there's derivative rules, which I'll actually tell you. Maybe I answer a question that I think was on Piazza that I don't know if the TA's answered or not, but in this course, you will get a formula sheet on your midterms. So a lot of these things, like any of these rules, even this rule, I think, will be on your formula sheet. And there's more derivative rules, such as like the derivative of an exponential, x to the a, is just, of a polynomial for some general power a is just a times x. This is wrong. I don't know what was going on there. Hopefully that's not on your formula sheet. Or if it, yeah, okay. Obviously that's what's happening here. So you reduce this power by 1 and you put a in front. And for exponentials, it's just literally the same. Like the derivative is just the same, which is really cool. That's one way to characterize the exponential. It's the function that when you take its derivative raised to some power, it's the same function. And then the logarithm's derivative is like this 1 over x thing. Okay, and then the only other property you need to know about these derivatives is there's this operation called the chain rule that you will use a little bit later when we have to optimize some things. And the chain rule says that like if you have a function that's composed with another function, then you can break up its derivative into multiple parts, and then you only really need to apply these rules that we've seen above. Okay, and that looks like this, for example. So like if you have some function f of x that's actually a function like g of h of x, then its derivative, f prime of x, can be written as the derivative of the outer function with respect to the inner function as like the input to it. So you treat this as like the variable, and then you take the derivative of the inner function with respect to its input, which is like the x. And so like if you, for instance, have the function e to the x squared, notice this looks like a composition. It looks like the exponential function composed or applied to the h function, where h here is x squared, and then the chain rule would say, well, what's the derivative of this? You don't have a rule for this function up here, but you have the rule of its like parts, you know? And so let's do it. So first of all, you take the derivative of the exponential function with h treated as constant. We know what that derivative is, just going to be the exponential. So that's why g prime is just the exponential of that. And then you take the derivative of h of x, which is 2 to the x. And so your final derivative is the 2 multiplied. That's what you get. Okay. And, okay, so great. But you can imagine, you know, these are functions of one variable so far. But since we're going to have a lot of data points and a lot of features, you can see that we're going to have multiple dimensions, kind of. Like, you know, there's these d-dimensional features, there's n data points. We're going to probably want to know how do things change as we change like one data point or things like this. And so we're going to need to talk about derivatives of multivariate functions, which are called partial derivatives. And so this will be important. I guess it all builds on the step before. And so, yeah, the derivative or this partial derivative you should think of is like the derivative of this multivariate function with all variables fixed except for the single variable you care about looking at its rate of change. And it's written like this. So instead of using this like, so, okay, above here you saw this like, this is like normal lowercase d symbol, df, dx. Well, now we use what is like called del f and del x1. And this symbol, I guess, kind of looks like the number 2. But this is to denote it's a partial derivative. And so, yeah, if you have some function of like x1 and x2, then its partial derivative, which is always in terms of a single variable, is written as like the partial derivative of f with respect to that variable you care about. And then you produce a function, which we'll see in a second, which can in general be a function of all the inputs you started with. So let's look through an example to see how this works. And just to quickly answer the question, someone's like, do I need to rewrite these notes or can we listen? What's the most effective way? I don't know what the most effective way, to be completely honest, because in my undergrad, I didn't take any notes at all. So, and no one shared the notes either with me, so that was never great. But I'm sharing all the notes, and you have the videos, so it's up to you. And maybe why this is being partly asked is also like, I can definitely imagine that this is kind of not so exciting, that all of it's already written and I'm just like circling things on the screen, and this is kind of like slides, sort of. And the reason is to get through this math stuff sort of quickly because there's lots of other things to get to. And when we get to the supervised learning stuff, 3 lectures from today, I will actually be writing a lot more on the spot, and there maybe that'll be better to follow and so on. Hopefully that answers the question. Okay, so back to business. These partial derivatives, let's do an example. This example, I guess, kind of tells you everything you need. So you have a function of 2 variables, x1 and x2. The function is 2 times x1 times x2 squared. Okay, let's look at its partial derivatives. So I need the way to take the partial derivative with respect to x1 is I treat the function as if it's a function of x1 and hold all the other variables as if they're constants. So this really just looks like 2 times this, these are like the constants, and then I just have a function of x1. So it just looks like a linear function of x1. And that derivative, we know, is just going to be the constant in front. So that would be like 2 times this, right? That's your constant. So that's what you get here. Okay, and notice here it's actually not a function of both variables anymore, it's just a function of x2. But now let's do it for the other case, which is let's take the partial derivative in terms of x2, right? And the way you think about this is like, if I have a function of multiple variables, I want to know how does the function change if I vary one of these variables. And this is going to be important because we're going to want to, we'll see, but we're going to vary the other variable x2. So what happens? Well, I treat the other things as fixed. So I'm going to treat I'm going to treat x1 as fixed, and so this thing is a constant now. I take the derivative, just apply the rule that the 2 comes out front, so I get 4 times x1, and the power gets decreased to just x2. And so you can see, I took the derivative in terms of just one of the variables, but at the end I still get a function of both of the original variables. And in general, this will be the case. Okay. Often you can imagine that when there's a lot of variables, this gets really tedious to write, especially when you're applying like the chain rule over these things. And so a lot of time when we write these things, we're just going to like exclude the inputs to it. And this will be fine. But you should always keep in mind, at the end of the day, this thing is still this multivariate function. Okay, so now let's just kind of end things with this last example, which is a slightly more complicated one, but one that you will see in the course a lot, because this is the example of like a linear function and using the dot product and so on. Okay, so pay attention here. So we have a function that's now looks like this. It has a bunch of inputs. It has x1, x2 up to xd. And you're going to see this also throughout the course. I think I mentioned this dot, dot, dot stuff just means like fill in with all the obvious indexes in the middle. And this is actually very, very commonly used in math everywhere. This is actually quite formal. So you write this like x1 to xd, w1 to wd. So this is a function of 2 times d variables. And it's totally fine to write something like this, which is a function of the x vector and the w vector, right, which are made up of this and this. And the function, now I define the function, I'm giving it a definition, which is I'm going to write it as like you just take every index, multiply them, and add up with other indices. So let's say this, x1 times w1, x2 times w2 up to xd times wd. You can rewrite this using the summation notation as follows. So this is a good like practice to get comfortable. Right, so here's your inside function, and it's getting summed from I equal 1 to d. And this is equal to exactly the dot product. So like all this notation, super important to understand these because this will be used a lot. And yeah, so this is called a linear function. Okay, and now let's talk about its partial derivatives. And the partial derivatives turn out to be super easy. Right, so let's do the partial derivative in terms of like the w's. And so we can do it for the x's as well, but let's just do it for the w's. So I want to take the partial derivative of one variable, such as like w1. So I look at the function, I hold everything constant. Look at this thing. It's like this thing's constant, like some other, oh, sorry, well, this thing's not, okay. Like everything else here is constant in the sum, because that has nothing to do with w1. And so you just have x1 times w1, and you want to take its derivative. Well, the derivative of all these constants is just 0. So you're just left with the derivative of x1 times w1, which is just x1. Okay? And then you can do the same thing for w2 up to wd, and you're going to get this xd. And believe it or not, this exact calculation will be very important very soon for like an algorithm called linear regression, in which what are we going to try to do? We're going to try to learn a line that best fits the data. The line is going to be characterized or described by its like corresponding kind of slope, which is going to be this w vector, right? And we're going to somehow try to find the w that best fits the data. And we're going to see later that you might sort of remember that to find like, you know, something that like, let's say best fits or like minimize, like we're going to find some objective and you're going to want to like minimize this objective. To minimize objectives, you'll like take a derivative and set it to 0. So this is where this is all going to come up. You're going to have some objective that's a function of this like parameter you're trying to find, and you'll be taking its derivative and setting it to 0. And so all these partial derivatives would be very important, because you're going to take all those partial derivatives and try to set it to 0, and that'll give you the corresponding value for your w. Okay, so that's how it all comes up. And in general, when we have a lot of partial derivatives, we use this thing called a gradient, which just puts them all into a vector. Okay, so the gradient is just a vector of all these partial derivatives. So if we had some like function of an x vector, then its gradient is just each of the partial derivatives put into a vector. Okay. And so we've already seen from this example, this like x2, x1, x2 squared case, you just take these two partial derivatives, you already calculate, put them in a vector. This is called the gradient. And that will be important for like these lines and more general functions later on. Okay, that's everything there is to know about math stuff and derivatives and integrals. And the next topic is going to be probability. And I maybe wait like 10 seconds to see if there's any questions before that. Okay, great. So let's move on to probability. And as with the math stuff, I'm going to try to motivate why we care about probability. Oh, and I have a bad feeling. Did I put these notes up? Oh, that's really unfortunate. Yeah. Let's see. I guess I will put them up right now. Why not? Yeah, I should really add a reminder to do this for the future as well. Okay, I have pushed the changes, so GitHub should build that page in like a minute and a half, and they will be there. But, I mean, in the meantime, I'm just going to be talking about the high-level idea anyway. So why do we need to learn probability? And the answer is going to be because that's where our data set is going to come from. And so like our data set is going to be what is called random, right? We talked about this thing, which is like in supervised learning, we've talked about like, you know, we have this like batch of labeled data, but we haven't really talked about what randomly sampled means. And I mean, like maybe to somehow like even more high level motivated than before I do this is like, at the end of the day, like who knows where you, like you get some data set, but who knows like what that data set is going to be. like, I don't know, that's like maybe somebody like purposefully chose a data set such that it's like really, really hard for you to learn or something like this. That would be called like maybe like adversarial data and so on. But we're going to make this like, I guess it's really called like an assumption, which is that, you know, the way the data came is it came from like you somehow randomly gathering it. Okay, so here's the example. You're like trying to predict these house prices in Edmonton. And the way you gather the data is you just like randomly set out some, I don't know, some questionnaire or some questionnaire and then got this information from people. And that's it. You didn't like ask your friend to go gather it who might have like purposely made it really good for you to like learn from, or maybe he was angry at you and like made it bad for you or something. So it was like what is called randomly kind of gathered. And we need to define this sort of formally because, you know, we're going to ask this question of like, I don't know what data set I'm going to get, right? Like I randomly gather this. That means like I gather like n feature label pairs, so like n house information and prices. But like, I don't know, I could get like really, really unlucky, and my random sampling of this could be somehow that I only get houses in Edmonton that have exactly 10 rooms. And that's it. Like that's possible. I go and like somehow the people I randomly chose all have houses with 10 rooms. And then I'm asked to like predict houses based on this data, you know, of any number of rooms. Well, like good luck. You're not going to do very well if you have this data set. And so the way we're going to kind of like resolve this situation is that, well, we're going to talk about doing well, like kind of on average, right? And so it's okay if we don't do well on this kind of case because it's like super unlikely that we get this really poor data set. Okay, and that's going to be the kind of idea that like we want to do well, and like the average data set we would get, which, you know, should properly represent kind of the distribution or whatever, the rough idea of the number of rooms and prices in Edmonton. And there's going to be all of these outliers that are like really bad data sets, but we won't worry about them as much because they're super unlikely. Okay, and the way this is going to be all formulated now mathematically, and then we're going to, I guess, define all this notation as before, is as follows. This like data set thing is now going to be what is called random. And here's how this is going to work. We're going to say that each one of these feature label pairs, okay, is written like this. It's going to be, this notation means that it's going to be randomly sampled from some distribution P. Okay, so just maybe to put it out there, like this could be like some, I don't know, some normal distribution or something like this, just high level. And you randomly, maybe that's like the distribution of houses in Edmonton follows a normal distribution. And so our assumption is going to be that each one of these like feature label pairs you gather is randomly selected based on some distribution. And all of them are actually independent of one another. And that assumption, this independence thing, we'll see what that means. But I mean, like, it really means what you think in English, which that one does not depend on the other. And this will be important for algorithms and for the math and stuff to work nicely. And that's really the motivation, because when we're going to talk about some of the math things, it's going to work very nicely. And this is like really the assumption that a lot of the algorithms do actually make, and it seems to be fairly good in various problems. And maybe just to make it very clear, this independence would mean something like, you know, when I gather a house, let's say I randomly like send this survey, someone gives, like I get information about a house, I will not then look at the house and be like, oh, that had 2 rooms. Let me like bias my next sample to like the part of Edmonton that's really rich, so I get a house with more rooms, right? So it's like, I don't do this. I'm not looking at, like, I just independently send them all out and gather data that way. And that is going to be the big change. However, what that is going to imply now is this very interesting property, which is now, okay, so that's really the only change that's happened in this picture, is now your data set is what's going to be called a random variable. And it's going to be defined in this way. So it's going to be this like multivariate random variable where each one of these data points is a random variable, okay? And the downstream effect of this is now the learner, right? This A guy, which is now producing my predictor, is also going to be what is called a random variable, actually. So it's going to take in as input, right, this random data set, and it's going to produce what we're going to call a random predictor. And so if the data set is like different, of course, we're going to produce a different predictor. And so since this learner and these predictors are going to be random, we're actually going to be able to talk about like what is the average predictor we produce, right? And this is what we're going to kind of like care about. It's like, what's the average model I produce? Okay, like of course, if the data set is really, really bad, I get really unlucky, I'm going to produce a model that's garbage. But I want to like, I'm going to want to say that like on average, the model output is going to be good. And that's where it's all going to be important. And that's going to be important when we talk about the objective, which is after probability. Okay, is there any questions about that? Because it's going to turn out there's a lot of notation and stuff to define probability and whatever. Okay, and there is one question online, which I think is actually good to point out, because this, I think I mentioned it before, it's said in the notes, but the question is something along the lines of like, why did we call something a feature and why did we call something a label? And we're going to see this a little bit more in the next lectures, but like, it's kind of arbitrary, right? Like right now, it seems kind of arbitrary. Like, for instance, why did I say the number of rooms was the feature and the price was the label? Right? It could have been the other way around. It could have been like, you give me a price of a house, I want to predict the number of rooms. And that's totally valid. That could be your problem too. And the answer is, the thing you call the feature and the thing you call the label is based on what you care about predicting. So if you care about predicting the number of rooms based on prices, then your features are going to be the prices and your labels are going to be the number of rooms. And so like, and the thing you usually care about predicting is the thing that's hard to gather. So it might be easy to like, you know, gather the number of rooms of new houses, but if they have never been sold, you're trying to like predict what price should I put it up for sale. So that's like the hard information for you to know, and that's why you really care about getting a predictor for it, right? And, yeah. So completely problem dependent, what you call a feature and what you call a label. And we're gonna like, I guess we'll see this with this probability stuff. Like some features could be completely useless. Like I don't know, like maybe like the like I don't know, the number of dogs in like the Netherlands, probably a useless feature for you to predict the price of houses in Edmonton, but you could add it. And yeah, and we'll see what the effects of something like that is later as well. Okay, so let's get into probability. So here's the story. There's going to be a lot of things we cover, and I'll explain them in a second, but the other thing I want you to note is like, you might think probability is obvious, or like it's super simple and intuitive. And if there's anything I've learned through my whole like time working in machine learning theory and with like probability is like central, is that this quote by Daniel Kahneman, who wrote the book called Thinking Fast and Slow, which some of you may have read, is like absolutely true. And that is that like humans have really bad intuition when it comes to randomness. You might think you're great when it comes to like, you know, understanding that like a flip of a coin is like 50-50, or like the roll of a dice, if it's a fair dice, is like 1/6 probability. But as soon as you have like, I don't know, some like function, like you care about maybe like the value of the dice squared, and you're like, what's the average value I'm going to get if I care about like the squared value of the dice? And then when you apply other like it just becomes super, like all sorts of things become unintuitive. There's all sorts of other things where like there's independence of things. You might think things are independent, but they're actually dependent and so on. So all this is to say is that if you think probability is very complicated when you start working with it, you're like not alone. Like this, I think this is one of the like hardest topics actually to grasp. And it's like, yeah, I feel it's like understated how confusing a lot of things can be in this topic. Because I feel like people have this perception that it should be very intuitive. Okay, anyways. So let's try to make it maybe somewhat intuitive or make sense. Okay, so here's the story. We're gonna like talk about probability, like there's these things called outcomes, events, distributions, we'll define them all. And then we're gonna get into like probably the most confusing topic of all called random variables. And it's because to define them formally, it's very unfortunately complicated, and so we're going to go with like a more hand-wavy one that is usually used in a lot of probability courses. And then we'll talk about ways to calculate probabilities, and we'll go over some other things. Maybe they're completely uninteresting now because they mean nothing, but we'll get there. And okay, at the end we'll get to things called like the expected value and the variance of objects, which you probably have some intuitive understanding of what that means, and we'll define them all. Okay, and I want to start with another kind of like disclaimer, which is like, if you find that some things are informal, that's probably because they are, and hopefully I will tell you when they are. And that's because, especially this random variable stuff, there's this, you may not know, there's a whole other branch of like pure math called measure theory. And measure theory defines a lot of things like a lot more formally than this. And yeah, and a lot of that is kind of hidden and also not told to you if you take a probability and statistics course sometimes. So just so you know. Okay, so now let's start with what this whole probability business is. And it's centered around this story of like, you know, you kind of do some experiment. It's like, I don't know, you like roll a dice. And I mean, you can do a science experiment too, but that's like more complicated, of course. We'll start with the simplest experiment. You like roll this dice. And like the outcome seems to like change and it's uncertain and sometimes it's this and sometimes it's another thing and so on. And so that's your like experiment. So that's your flipping of a coin and rolling a dice and so on. And you want to somehow like understand this experiment better. Like why am I getting this outcome and why am I getting this? Like how often do I get this outcome and things like this. And so as I've been using, there's this terms called the outcomes. So the set of all your possible outcomes from these experiments, right? Your experiments give you like an outcome. The set of all the outcomes is going to be described as a set, and this set is going to be called your outcome space. And it's just the set of all outcomes. So like for the case of the case of flipping a coin, you'll have like the outcome space of maybe 0 and 1, where 0 you've labeled as the number for tails and 1 is for heads. These are your outcomes. For rolling a dice, it'll be like 1, 2, 3, 4, 5, 6. Right? Okay. And for like the case of a line, like we were talking about this like classifying lines. Well, the wine, you're gonna get this, you're randomly gonna get a wine bottle or like information about it. And one of the information things or like pieces of information might be like the amount of a chemical. So like it could be any number, let's say from 0 to 900, because that's the most, literally the most like that wine bottle could hold of that chemical. I don't know, other things you want to like measure, I don't know, anything in science, like the volume of some, or like the weight of some object or something. Well, there's going to be like some sort of measurement error. You might notice that like if you measure the same object over and over again on the exact same scale, there's going to be some like error in the measurement just because of like, I don't know, the fact that the scale is imprecise or maybe some other things are happening at the time. So, okay, so these are all your possible outcomes. Now there's going to be a notion of an event. Right? And the idea of an event is going to be that like something happened, you know, like an example of an event in like English terms is going to be you roll a dice and you get either the number 1, 2, or 3, or you flip a coin and you get either 1 or 0, which is like you get something. And so events are just going to be sets of outcomes. They basically describe the set of outcomes you care about. And unsurprisingly, the next thing you're going to talk about is the probability of these events, right? The probability of getting any one of these outcomes. So that's going to be like the story. So yeah, events, all you're going to need to know is they're going to be these subsets of the outcome space. They can be a whole outcome space too. And that would just mean what is like the event that I get something. And the reason we define these outcomes, these events, and so on is because we're going to, at the end of the day, we want to talk about what's like the probability of something happening, and that something is going to be the event. Okay. And so we're going to need some function, which is going to be called a probability distribution, which is going to take as input an event and produce a number that tells us the probability of that event. And so I'm not going to define this object, but this, okay, so probability distribution, it's a function, right? I told you this, we've defined functions before. What is the set that it's taking inputs from? It's going to be a set of events. And that set is going to be called like the event space or the set of events, as I've said. And in general, you might think it's totally fine to just take that set of events to be any possible subset of the outcome space. So like take any set of outcomes, and that should be totally fine. And it turns out that's where all the problems come up. And we're not going to talk about any of these problems, but this is why like all this measure theory stuff becomes important and so on. And I'm just going to vaguely tell you that like for this course, you can just think about like an event can be any possible subset of outcomes, like of the outcome space. So like it's just a set of outcomes. And that's going to be totally fine. But the issue comes when we have what is going to be like an uncountable set of outcomes. Okay, so like in the case of this, if your outcome space is the following, then it's actually going to be a very big problem if you defined this set to be all possible subsets of it, right? Because it's going to turn out that you're not going to be able to, for mathematical reasons, define what is called like a uniform probability distribution on this thing, or you're basically not going to be able to define the uniform probability distribution, which is like, if you take like, let's say, like the event, which is like half of the outcome space, maybe you want to assign like half probability, well, you're going to have all sorts of problems defining this thing. And that's where measure theory comes up, and this object is not just the set of all possible outcomes, but it's going to be something called like a sigma algebra, and it has certain properties, and guess what? You're not going to need to know any of this. And so that was my little detour to saying that things do get a little more complicated, but all you need to know for this class is that, once again, an event is just a set of outcomes. Okay, and so this set is just like going to be the set that contains sets of outcomes, right? The events. And it's going to map you to a number 0 to 1. Okay. There is some, maybe, do I have an example of this first? It should be here. Let's look at an example first, and then I'll tell you about the properties it should obviously satisfy. So this is the case where you have like the dice, or sorry, the coin flip. So your outcome space is just the possible outcomes you can get, which is like tails or heads, right? Now the events are going to be different like things that you might want to talk about. So you might want to talk about what is like the probability of getting nothing. Okay, that's going to be the probability of the event that contains nothing. Notice probability of an event, so the probability takes an event and gives you the corresponding probability of it. The probability of getting nothing is 0. Okay. What's the probability of the event, which is the entire outcome space? This is to be read, this is the probability of you getting either 0 or 1. Well, obviously that probability is 1. Like you're either going to get one or the other, right? And then there's the two more interesting cases, which is like, now for a fair coin, what's the probability that you get tails? That would be the probability of this set, which is like the probability of 0. And that's going to be 1/2 for a fair coin. And for getting the value of 1, it's going to also be 1/2. If it was not a fair coin, right, like let's do an example, and this leads you into the natural properties of that these probability distributions will have, which if it's not a fair coin, maybe you get tails with probability 1/3, right? Well, like, is it possible that I get heads with probability 1/3 as well? Right, this is going to be a problem because, I mean, I can only get heads or tails. I'm going to get one of them. So obviously, if you take up all the possible like outcomes and sum them up, it's got to add to 1. So anyways, so this has got to be 2/3. And this is going to be like the properties that your probability distribution kind of needs to satisfy. So that's just really high level explaining. There's like 2 properties you need to know. Which is, first of all, that the probability of the entire outcome space, right, which is an event in itself, right? The outcome space is just a set of outcomes, so that's an event. And that is to be read, the probability of you getting any outcome is 1. And the other property is that if you take some event, okay, this is how we're going to use the notation we're going to use for events, this like calligraphic capital E symbol. If you take any event that's a subset of the outcome space, and everywhere here, last year I used, okay, let me just point this out now because I'm sure I'm going to forget about it later. Last year I used like this notation without the underline thing for subset. Now, throughout this year, we're going to use the underline everywhere. So some places you'll see this, it means this. These are like, for the purposes of these notes, these are equal because I'm probably going to forget to update it properly. Okay. So anyways, it's read as, if you have an event, right, that's just a subset of the outcome space, and you have another event that's a subset of the outcome space, and they're what is called disjoint. So they have outcomes, they don't have any outcomes that overlap. Now, using notation that we've learned, this is good practice, that would mean that their intersection, which says how many outcomes do we have that are the same, that's 0, that's the empty set. Right, so you have these 2 disjoint events, they have different outcomes. Well, the probability of this event unioned with this, right, which is like, you take both sets of outcomes, you combine them into one set, which is now this larger set of outcomes that you want to ask, what's the probability of getting any one of these outcomes? Well, that probability has to be equal to this probability of the sum of them. And this is like very natural, right? If you have like Like this is exactly what this property was. This y, let me just write it, right? This guy, what is this? This is the union of 0 and 1, which are two other events. These are disjoint events, right? They have no overlap. And their union, we know that that probability of this union is 1. And the property above says if you break them up, right, into two events, which is like this and this, then this probability should be equal to the sum of the two probabilities, which is this. And so if one of them is 1/3, the other has to be 2/3. Anyways, it's just like stating this obvious property. Okay. And this gives you this one more other like useful property, which is that, you know, if you have some event like this, let's look at the picture here. Then if you have the probability of this event, then you can talk about, well, maybe we want to know about the probability of everything other than that event. So like the complement of the event, that's going to be all this orange stuff. And unsurprisingly, since we know the probability of everything in the outcome space, like that event, the probability of z is 1, then the probability of the complement event should be 1 minus, right, the probability of the original event. And so it works both ways. So like, yeah, the probability of an event is equal to 1 minus the probability of its complement. Like maybe for the dice roll, we'll see this for the dice roll case in a second. But for the dice rolls case, this would be like, imagine your event is like, what's the probability I get 1? The roll of a 1, right? That's my event. Well, then that's the same thing as saying, but like that probability is going to be the same as 1 minus the probability that I get any number greater than 1. So like 2, 3, 4, 5, 6. And that would be the complement event. So maybe just to make that precise, like if your event for the dice rolling case is equal to getting the number 1, then the complement, right, as we've learned, complements of sets is everything that's like everything in your universe here, which was 1, 2, 3, 4, 5, 6, excluding what's in the original event. So that would be 2, 3, 4, 5, and 6. And so now if the probability of this is like 1/6, let's say, then the probability of this thing is going to be 1 minus 1/6, which will be 5/6. Okay, and so now we're gonna say one more thing about these random like dice rolls and see that we immediately start stumbling into some very annoying issues with trying to define probability distributions. Okay, so the dice roll example has this outcome space, right? 1, 2, 3, 4, 5, 6. There's lots of events here, right? The events, once again, are take any set that contains outcomes. There's a lot of these subsets of this object. In particular, like 1 is an event. The set containing 2 is an event. The set containing 6 is an event. Let's say the probability of each one of these is 1/6. Well, then you have other sets like 1, 3, 5. What's the probability of that set? Well, it turns out from the property we saw above, we can break it up into the probability of 1, probability of 3, and the probability of 5, right? Because this object here is equal to, 1 union with the set 3, union with the set 5. Okay. And so you can see there's lots and lots of events. And if we were to even like try to plot this like probability distribution over events, right, which is what it's talking about, then it would look like it would be a giant x-axis. It would be like, oh, for the, empty set, you get, the probability is like 0. For any one of these events, which is like just a single dice roll, well, that's 1/6. For the event that you get a 1, 3, or 5, well, that's like 1/2. And there's lots and lots of other possible events. And so it becomes kind of annoying. You have to define all these things for your events to define your function. You probably don't want to do this in general. So like, what's the kind of solution? And the solution is going to be that, well, like roughly speaking, you're only going to need to define it for all of these like singleton events, which are the events that contain only single outcomes. And we're going to see that this is going to give us what is called like a probability mass function in a second. And like building up to that as well, as we're getting there, we're also going to see that there's like this maybe sort of unnatural way of writing the probability of something, which is like, I'm plugging in an event in here, right? But at the end of the day, you're not getting like this, like when you roll a dice, you either get 1, 3, or 5, right? And so you roll a dice, you get some like random outcome, which might be any one of these numbers. And this is to be interpreted, right, as like reading the probability that your random roll belongs to this set. It's like 1, 3, or 5, and so on. And so roughly speaking, that's going to be the motivation for defining a variable for your like kind of random roll or your random outcome. And this is going to be called the random variable. Okay, so it's going to be like a variable that describes the outcome you get when you like roll this dice or whatever. Okay. So anyways, yeah. So random variable is going to be like a variable that takes values in the outcome space. And the important part is it's also going to have like a probability distribution associated with it, so that we can talk about things like what is the probability that this random variable takes the value of, let's say, 1, or what's the probability this random variable takes the value of like 1, 2, and 3, and so on. Okay. And so yeah, an example of this is going to be like, we're going to have a random variable, which is now going to like be an element of the outcome space for dice rolls like this, or a random variable for heads or tails. And we'll use capital letters for random variables everywhere. And okay, the other thing, before showing examples of this random variable stuff, I wanted to mention again that this like random variable stuff, I guess this is how it's like brought up in probability courses. But in reality, it's actually not like random or anything like that at all. And it's actually like a function in measure theory world. And sometimes maybe people will explain it this way too. I chose to avoid it, but I thought I'd mention it like as a side note, which is like this random variable thing like is actually like in the background is the whole idea is that, you know, you have these outcomes that at the end of the day are like, they're kind of like arbitrary looking objects, you know, they're like maybe like your random variable is like some pictures, and like I don't know how you like this picture might be like what you see of the picture, and like for the dice roll case or for the flipping of a coin, it might be like heads or tails or something like this. And so this random variable is just going to like kind of, it's going to be this function that encodes, that maps outcomes to certain numbers or objects that describe the properties you kind of care about. And so like for the heads or tails thing, it's kind of obvious. It'll map like tails to maybe 0 and heads to 1, which is what we've been seeing. But there could be like other ones that like for the dice roll case, you could have the random variable that, for instance, like describes, you know, even or odd numbers. And you might encode even numbers as the number 0 and odd numbers as like the number 1. And you might talk about like what's the probability that this random variable, which now describes this property, has some things. Anyways, that's kind of the background story of this. But for us, it's just like random variable takes values in some outcome space, and it has some probability distribution associated with it. And we'll see how to make use of it in a second. Okay, so this is how we're going to work with these random variables. So as above, you have some outcome space, you have some random variable. It's just a variable, it's just like an element of your outcome space. And before we were talking about things like what's the probability of an event. Well, now the common notation you'll see being written is the following, which is like you'll write, the equivalent notation actually is like exactly the same as you'll write, what is the probability that this random variable, which is like the random kind of outcome of my experiment, takes on an element in this event. Okay, so this notation is like exactly identical. And people will write things like this. And so similarly, you can see that like the probability of like getting it, let's say the numbers 4, 5, 6, can be written as the probability that your random variable takes out, like takes values 4, 5, 6. And then we get into like more informal notation that gets used and simplifies things, which is like this. People write like, what's the probability that my random variable is greater than 4? Okay. And what you're going to need to know is that the definition of this is that it means that this random variable takes an outcome which is like 4, 5, or 6, because those are all the values that are greater than 4 or equal to 4, right? And people write things like, what's the probability that my random variable equals 4? And this really means, behind the hood, what is the probability of the event that X is an element of the set that just contains 4? And so you'll see this notation very often. Okay. And we already saw like notation kind of for this data set stuff earlier, but well then, like once again, this random variable is somehow this like random outcome that you're getting based on some experiment. And some of that experiment has like some distribution, right, which tells you the probability of getting any outcome. And so this notation here, like random variable, this tilde symbol, I guess, P, is to be read as like this random variable is sampled from P. Or sometimes people will say like this random variable Z is associated with like probability distribution P. So this is their relationship. Okay. And so now we want to like, okay, now we're going to get into like the thing I was saying before, which is defining distributions over events gets really, really ugly because, you know, here we only have like 6 outcomes and there's already a ton of outcomes that you have to define its probability for. And I said there's going to be like this nice shortcut that you just define the probability distribution over like these events that contain single outcomes. And this is all going to be great and it's going to work fine until we get to outcome spaces that are like infinite. So like if you have an outcome space, like let's say, well, if you have an outcome space like the real numbers, this is going to be uncountably infinite. And we're going to run into this problem of just defining the probability on each thing, which I will explain why in a moment. And so for this reason, to basically handle the cases where things are uncountably infinite, and for the cases where things are countably infinite or finite, people define 2 types of random variables called discrete and continuous. So discrete is going to be referring to this countably infinite or finite case, and continuous is going to be referring to the case where the outcome space is uncountably infinite. And the reason why is we'll see that the way to define distributions will be different, and we're going to have to handle it differently, and we'll see some motivation for that. Okay. So we start with defining this object called a discrete random variable. Yeah, like all you need to know is really this, that our random variable is discrete if its outcome space is countable. And that means it's countable or finite, basically. Countable means that it's also finite. Okay, so like the natural numbers are, for instance, a countable outcome space that you can use. And there's this other case, which, you know what, like, is not super important. You can read about it more in the notes and so on. But yeah, so for now, just like think about it, it's just the random variable is countable. The random variable is discrete if the outcome space is countable or finite. And so here's some examples of discrete random variables. So like the random variable describing your coin flip. The outcome space is just 0 and 1. That's a discrete random variable. For the roll of a dice, it's 1, 2, 3, 4, 5, 6. That's a discrete random variable. And that's all you need to know for this discrete random variable stuff, really. And there's this extra caveat that about this like uncountable stuff that you can maybe read in the course notes. It's not that important. Okay. And then the other version of random, like the other case, is the continuous random variable, which is when your random variable is continuous if it belongs to an outcome space that's uncountably infinite. And examples of this is like your random variable belongs to the interval 0 to 900. Okay. And another example is like your random variable belongs to the real numbers. Okay. Now, I want to like point out something which is going to be the stuff on the right about the probabilities of these uncountable things and how they're going to cause some problems. Okay. So let's look at this. So like, well, we know the probability of this event, which is like the whole outcome space has to be 1, right? And that event is to be read that like the probability that I randomly sample some number between 0 and 900, that's this event, or this probability, that's going to be 1, right? Like I got to get something between this interval. And now the question becomes like, what is the probability? Like, okay, and then I can define like the probability of like maybe the interval 0 to 500, and that'll have some probability and so on. And then you can start defining smaller and smaller events until you get to the events that contain just like a single outcome, like a single number, right? And so then you might ask like, well, what's the probability that, well, my random variable takes on exactly some number? Okay. And so it turns out that the property of these like uncountable or like these continuous random variables is that the probability of this is actually going to be 0. And this might seem really weird. And the answer, like how this is going to work, we're going to see like some examples of like how this might work, but like the intuition is like, this interval has like an uncountably infinite set of numbers. And so like, if you like assigned a number to a probability to every single number, well then if you like summed it up, it would sum up to more than 1, essentially, right? So it turns out that like, we're not going to allow you to assign anything to any number, but you're going to assign you can assign probabilities to like intervals, but not to like any particular number. And we'll get to like maybe an example that makes this more intuitive a little bit later, but that's going to be an important defining property of these continuous random variables. So their outcome spaces are uncountably infinite, and they also have the property that any event that has a single outcome in it is exactly 0. Okay, and so these are going to be your continuous random variables. And I guess we probably should end now, but what we'll see in the next class is that the reason to define these random variables is because if we want to define this probability distribution, we should handle it very differently. Okay. Well, thank you, and I'll see you on Thursday.